quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Okay, hello everybody. My name is Joel Jones from the PUCP in Lima, Peru, and I'll be today's host of this webinar in the Latin American webinars of physics. Today we have a very interesting talk about neutron-antineutron oscillations in supersymmetry. But before we begin, let me remind you that you can ask questions via the Q&A in Google+. These questions will be answered at the end of the talk. Or you can use a hashtag to ask us questions on Twitter. The hashtag is this one. This one, LAWAP. Okay? So that's that. Remember also that if you miss any live transmissions, you can watch the transmission later in our YouTube channel. Let me tell you also that we have a WordPress page where we also centralize all the information. I think you can see it right there. Okay, it's not very difficult to remember, right? Law Physics, WordPress. So okay, let's get to business. The speaker is Lorenzo Calibbi, and he's currently a senior research associate in the Institute of Theoretical Physics at the Chinese Academy of Science in Beijing, China. So he's practically giving this webinar close to midnight. So I guess we should be very grateful for Lorenzo to give this talk, right? So Lorenzo received his PhD from the University of Padua and has carried out postdocs at CISA, at the Max Planck Institute, and the Université Libre of Brussels, right? And the title of his talk is Neutron-Antineutron Oscillations as a Probe of Supersymmetry Beyond the LHC. So let me present Lorenzo. Let's see, present to everyone. Here we go. We're all yours, Lorenzo.
Hi to everybody. Thanks, Joel, for the presentation. And yeah, thanks for inviting me to give this seminar. So I think now I should just share my screen somehow and show you my slides. Can you see it?
Everything good, everything good.
Okay, so here we go. I'm going to present recent work that I've done in collaboration with these friends who are both theorists and experimentalists from the Universities of Gothenburg and Stockholm in Sweden. So as Joel anticipated, the topic is neutron-antineutron oscillations. So why to study such process? So of course, this is a process that violates the baryon number by 2 units. And we know that baryon number is just an accidental symmetry of the standard model of particle physics. Basically, the Lagrangian of the standard model is invariant under baryon number just because you cannot write any baryon number violating operator respecting all the other symmetries. Nevertheless, it is actually violated, it's broken by non-perturbative effects. But this gives very tiny possible visible effects. So in a sense, if we observe any process violating the barrier number, it's a clean signal of new physics. So this is the first reason why we might be interested in looking like processes of neutron to anti-neutron oscillations. Furthermore, we know that barrier number violation is one of the requirements for having a successful baryogenesis, so to produce the baryon asymmetry in the early universe that then we observe today. So we expect that any extension of the standard model of particle physics will give substantial baryon number violation for this reason. A first process that we can think of as baryon number violating process is, of course, proton decay. As we know, this has been searched for since many years, and present constraints are already very stringent on the lifetime of the proton. And this process is, of course, requires the violation of baryon number by 1 unit, but also violation of the lepton number, simply because for conservation of spin, basically, a proton cannot decay to anything else than a lepton. So if instead we have a theory that gives substantial baryon number violation but no lepton number violation, the only new effects we can observe arise at a level of delta B equal 2. So violation of the baryon number by 2 units. And processes of these kinds are precisely neutron anti-neutron oscillation, and as we will see later, possibly also dinucleon decay, so the decay of 2 nucleon particles inside nuclei. The main motivation for studying these processes, or for reviving this process that has been studied quite extensively in the past, but not so much lately in recent years, is rather experimental. So that was our starting point. Why? So the present limit on neutron anti-neutron oscillation using free neutrons is this one. It's a limit on the oscillation time of the order of, as you can see, 10 to the 8 seconds. And it was established already more than 20 years ago by this experiment in Grenoble in France. And this is a sketch of what was the experimental setup. More recently, Super Kamiokande in Japan established an indirect limit based on the observation of so based on the fact that, as you know, they have a big tank with a lot of water, so this means a lot of oxygen, so they can set a constraint on the oscillation of neutron bounded within oxygen nucleus. Then, relying on some nuclear physics, you can translate this bound, that, as you can see, is very, very stringent in terms of lifetime, but the process is as we will see in a minute, are very different if the neutron is a free state or it's bounded in the nuclei. It can be translated to a bound on the oscillation time as a free neutron of the same order of magnitude of the Grenoble experiment, slightly more stringent. Of course, this translation involves some nuclear physics uncertainties, but it should be pretty robust. So our motivation was that there is a new facility under construction in Lund, in Sweden. It's a European project. It's called the European Spallation Source. It's a multi-purpose neutron source that will be mainly used for physics. But there's also a proposal to employ this source of intense neutron beams for new experiments on neutron to anti-neutron oscillations. So this is also why my collaborators in this project were all people working in Sweden, by the way. And so this project has not been within and we aim at improving the specificity on neutron oscillation probability by 3 orders of magnitude. So quite a remarkable improvement, which translated in a limit on the oscillation time will be a factor of 30 or so. So this is a sketch of the proposed experimental setup. Here you have the neutron source. Then the neutrons are guided within a pipe, vacuum, of course, and they are let fly for about 100 meters. There is a magnetic shielding, as we will see in a second. This is an important requirement for this experimental setup. And finally, so we can detect this process. A very simple equation. So this kind of Hamiltonian matrix is very familiar, for instance, to those who work in neutrino physics. Here we have the energy of the neutron, the energy of the anti-neutron, and some mixing terms. Of course, this mixing is an interaction that violates the baryon number, and it is required to induce our process. So from this, we can calculate very similarly to neutrino oscillation the probability that a neutron after a time of flight t oscillate to an anti-neutron. So as you can see, this probability gets suppressed by this delta E, which is the energy difference of the neutron and anti-neutron states. So this is the reason why this experimental setup requires a magnetic shielding, because the energy difference given by the Earth's magnetic field would be enough to decrease, to suppress this transition probability to unobservable levels. And by the way, this is also the reason why in nuclei, where of course a neutron and an anti-neutron feels very different potentials, the transition probability is so low that an experiment like Super Kamiokande can set, I mean, even if it can set such a huge bound, then this just translates to 10 to the 8 seconds in terms of free neutron oscillations. So how can be induced a mixing between a neutron and anti-neutron? Of course, we can just work in low energy effective theory, writing effective operators that can give rise to this kind of mixing. The simplest are of this kind. So you see these are six quarks, effective operators, possibly of different chiralities. So this means that these are at least dimension 9 operators. There is a full basis of operators. If you write it in an SU2 invariant way, you will see that there are possibly 14 combinations of 6 quarks operators up to mass dimension 14, because of course for SU2 invariance some of these operators require insertions of Higgs valve. What can be the underlying new physics, so the UV completion giving rise to operators of these kinds at low energy? In this work, in order to have a definite renormalizable setup and to compare basically the discovery potential of these new proposed experiments with other kind of experiments, for instance, high energy collisions at the LHC, we worked in a very well established concept, namely supersymmetry with R parity violation. R parity violation, of course, is required because the supersymmetric Lagrangian would be baryon number conserving if R parity were exactly conserved. So we did the simplest possible choice. So we extended the minimal supersymmetric standard model just with one set of operators, those precisely that violate R parity and the baryon number. So you can see here we have 3 quark superfields that then translates in the Lagrangian in interactions between a scalar quark, a squark, with 2 ordinary quarks. If we write only this new term in the superpotential, we have no lepton number violation, at least at the perturbative level. So this means that, as I was mentioning before, no proton decay can be used. But this term violates the baryon number by 1 unit. So we already see from here that we will require this kind of interaction twice in order to induce 2 units of baryon number violation. And given this tensor structure, these are SU3 indices. So this is a SU3 contraction in order to have an SU3 singlet. This is a totally antisymmetric tensor. We can see that these terms do not vanish only if these 2 fields are different, namely if the flavor indices of these two quarks or squarks are not the same. In other words, the terms inducing binary number violation, we required flavor mixing, flavor violation too. So again, this is our model, and as I was mentioning, flavor violation will be required in order to generate an n-bar oscillation. So a first constraint that we will have to take into account comes from flavor physics. So rare flavor and CP violating processes induced by supersymmetric particles in the loop, for instance, in a meson oscillation, KK bar mixing, BB bar mixing. This will be a first constraint. Second set of constraints will be given by other processes that violate baryon number, namely dinucleon decays. So two protons or two neutrons in the nuclei decaying, for instance, two kaons or two pions. These kind of processes have been searched again by Super Kamikande, observing possible decays, of course, of oxygen nuclei, and they can be translated in lifetime of protons or neutrons, diprotons or dineutrons, again of the order of 10 to the 32 years. So these processes can set relevant constraints on the parameter space. And then, of course, we are dealing with a supersymmetric setup. So we have these new supersymmetric particles, squarks, gluinos. So we will have to take into account constraints coming from direct searches for the production of these new particles at the LHC. But we are in a R-parity violating setup, so as you know, the lightest supersymmetric particle is not stable anymore, which means that we are not going to deal with the more canonical SUSY signature based on a large amount of missing energy at collider. So the collider phenomenology will be quite different, as we will see in this slide. So we have squarks and gluinos. They can both now decay to ordinary quarks. So this means that at the LHC, they just will give rise to jets. For instance, this scalar quark, this squark, can simply decay to two quarks, given our parity violating interaction lambda double prime, and this is very simple expression for the decay width. And in this figure, I'm showing the squark lifetime, so the squark decay length, rather, as a function of this baryon number violating coupling. So here we have 10 to the minus 5, and I'm taking lower and lower values down to 10 to the minus 10. So depending on the decay length, so how fast is the decay of this particle, we can have different regime, different phenomenology within an LHC detector. So if the interaction is strong enough, namely above 10 to the minus 6 or more for this new Yukawa coupling, the squark will just decay promptly. So the two jets will appear as coming from the interaction point. While if we lower this coupling, the square gets more and more long-lived and gives rise more likely to displaced vertices. Namely, it travels through the detector for a while, through the tracker, and then decays. So the two jets points to a displaced vertex, a vertex which is at a finite distance from the primary interaction vertex. If you lower more and more the coupling, eventually these objects will result as stable on the detector time scale, which means that it would look like what people call R-hadrons. So it's a relatively long-lived, strongly interacting particle, which will hadronize. We will form bound state with ordinary quarks. So it will look like a heavy colored object hitting the material of the detector at any place and eventually leaving the detector. So for the three of this kind of regime, there are, of course, dedicated searches at LHC experiments. So these are very different possible phenomenologies. The same we can say about the gluinos. If the gluinos are the lighter than the quarks, they can still decay to quark through this with the mediation of a off-shell quark with a virtual quark. So this is just an ordinary SU3 interaction, and this is our apparently violating coupling. So this is a three-body decay, and so it's further suppressed by phase space. So this is the reason why, on average, gluinos tend to be, if lighter than quarks, tend to be more long-lived. Here, if you can see, I start plotting from 10 to the minus 2. So the lifetime depends also on the ratio between quark and gluino mass. But as you can see, below, say, 10 to the minus 4, the gluino tends always to be long-lived enough to give rise to displaced vertices. So only for very large parity violating coupling, we will have prompt decays. And in general, even if the gluinos are heavier than the quarks, they will still decay through this diagram. This time much more efficiently. This decay will be on shell. So you can see that pair producing two gluinos will give rise to events with 6 jets. So we can expect a substantial, quite high jet activity in the signals for this kind of parity violating setup. So to summarize, what we expect at the LHC are to constrain this kind of models is absence of missing ET and either events featuring many jets or long-lived hadrons or displaced vertices. So we have to look for the appropriate analysis performed by Atlas and CMS in order to set the constraints of the LHC on our parameter space. We had basically to recast the bounds given by the two experimental collaboration on our hadron, so long-lived colored superparticles, displaced vertices. So this we employed a recasting done by these two gentlemen in 2015, where you can see for certain ranges of the in this case gluino to 3-jet lifetime, CMS analysis can set already constraints which are quite strong, the order of 1.4 TeV. And then in case our objects decay fast enough to give rise to prompt jets, we had to employ multi-jets searches from Atlas. And we also used the constraints by CMS on dijet production, namely to constrain the squark per production. In this case, this can give a bound on the squark mass of the order of 300 GeV or so. Okay, so let's come back to our N-bar oscillation process. As an example, I will just consider this diagram that was for the first time proposed by Stirner already long ago, as you can see. So this gives rise to our 6 quarks operator. As you can see, in this case, all right-handed quarks. And third thing that we observe is here we have our parity violating coupling. So this here, this is the two vertices that violate baryon number. And as I was mentioning, we, in order to this coupling to be non-vanishing, we require flavor changing. So the squark here must be either second or third generation, so a strange or bottom squark. This means that since we have to go back to the first generation, because in our operator, of course, we require only first generation quarks, we also require flavor mixing. So a mixing between second or third generation squark with the first generation squark. And here we just exchange a gluino. So these are just SU3 gauge interactions. So in the end, we can integrate out the supersymmetric particles, which are of course much heavier than the energy scale of our process. We obtain this operator, and the coefficient of this operator can be written like this in terms of our high energy parameters. Again, we can see 2 times the baryon number violating coupling, 2 times this parameter that parameterizes the flavor, the squark flavor violation, the suppression given by the supersymmetric masses, gluino and squark masses, and SU3 interaction. And then we can simply use this coefficient to estimate the oscillation time, which just results just given by this expression. So 1 over the value of this coefficient times an hadronic form factor, which is our main source of uncertainty in this business. So we know that this number has to be of the order of the sum powers of the QCD scale, but there are no definite prediction for this, not even from lattice QCD. So let me plug in some numbers in order to get a value for the oscillation time of the order of the present bound. We need, as you can see, a supersymmetric particle of the order of 1 TeV, 500 GeV for the quarks. Radar small baryon number violating couplings are sufficient. I'm taking this value for flavor violation, and as I was mentioning, I'm taking the hadronic form factor of the order of, for dimensional reasons, 6 powers of the QCD scale. As I was mentioning before, we have other constraints to take into account, which comes precisely from this, the flavor violation and, again, the baryon number violation. So flavor changing neutral currents, so we can write diagrams like this, so box diagrams that gives rise to KK bar and BB bar mixing. Of course, if these flavor violating parameters are complex, this can give rise also to CP violation in KK bar mixing, and the dinucleon decays. So if we have this lambda double prime UDS, we can write a diagram like this that allow decay of 2 neutrons or 2 protons to kaons. In case we employ the coupling involving the third generation, the bottom, just for kinematical reason, the nucleons cannot decay to B mesons. But of course, we know we have, for n bar oscillation, we need flavor mixing. So we can employ the flavor mixing to write a diagram like this that gives rise to decay of the dinucleon 2 pions. So our approach was defining some simplified models. So rather than having a definite top-down SUSY breaking scenario, we just worked with simplified model at low energy, defined only by the supersymmetric particles and interactions we need in this diagram. So we could compare in pretty straightforward way the strengths of all these different experimental informations, all the impact of all of them on our parameter space. And our goal was basically highlighting the complementarity of our neutron oscillation experiment and the direct LHC searches. So let me show you some colorful plots. Here I'm employing in this left panel the coupling involving the second generation, here the third generation. I'm setting this value, this intermediate value, 10 to the minus 6. It's a Yukawa coupling, so in a sense, we can expect some Yukawa couplings to be small if you think of the Yukawa coupling of the electron, for instance, which is more or less of this order of magnitude. And then here we just show the plane of the squark and the gluino masses. So first of all, our NN bar, present NN bar constraint is given by this blue line, and the expected increase of the sensitivity of the proposed NN bar experiments should test this region up to this dashed blue line. But of course, we have other constraints. The strongest in this case comes from dinucleon decays, which seems to be more or less of the same order of the proposed increase of the sensitivity in NN bar. But we have to take into account that, as I was mentioning, both processes are affected by strong hadronic uncertainties. So here I'm just plotting the central value, but you should rather think at these curves like bands which overlap and can span a little bit of this parameter space if you vary this hadronic form factor by an order of magnitude or so, since we don't know much about its actual numerical value. Then we have these colored red regions, which show the constraints, the direct constraints from the LHC on the parameter space. These green ones, which are in this part of the plane where the squarks are lighter than the gluinos, come from prompt decays. So basically, you pair produce squarks or you pair produce gluinos, and you obtain bounds from dijet and multijet searches. Dark green is multijet, and this green one, which does not depend on the gluino masses from direct squark production and bounds on dijet. While on this part of the plane, well, the gluinos are the lightest particles you can produce in strong interactions at the LHC. The particles tend to be longer lived, so the main bounds are given by the searches for displaced jets. This yellow region here, as you can see, is pretty strong. Goes up to 1.4 TeV for the gluino mass. Then, if you have a maximal CP violation in KK bar mixing, all the region below this red line is excluded by epsilon k, so by CP violation in KK bar. Of course, you can reduce this constraint if you assume that the phase is somehow suppressed. Well, on the other hand, the flavor constraints is not so strong in the B sector. So in case of you have this interaction, the constraint from flavor comes from BB bar mixing, so which constrain only this region. So you see that you have your parameter space is much less constrained. You have much more room for improvement, in a sense, from NN bar alone. And also the dinucleon decay is less constraining, because in this case the dinucleon cannot decay directly to kaons, but they decay to pion through flavor violation. So you have a further suppression of the process. So you can see here you have, of course, for this setup, the parameters, you have a quite promising situation, but already the NN bar constraint is pretty strong, tend to be stronger than the constraints set by the LHC, at least on the squark mass, already at the level of 1 TeV, and the future constraint can be up to go up to 2 TeV or so, which is a value which is maybe even beyond the reach of the LHC itself. On the other hand, if we take this R-parity violating coupling and we lower it, in this case by 2 orders of magnitude, the situation is reversed. All our low energy processes are not sensitive anymore, so the constraints are not are irrelevant, while LHC gives the strongest constraint. In this case, also the scores are always long-lived. Tends to be cannot decay prompt because the coupling is too small. The decay is too slow. So also in this case, we have also a constraint from displaced vertices on Squark, which gives a bound about 1 TeV, and one of the strongest constraints on supersymmetric particles so far. So a constraint on long-lived gluinos, which is more than 1.5 TeV on this part of the plane. So as you can see, I mean, here we have really an interplay between this kind of low energy test of this kind of models and the high energy test of the LHC. Depending on the regime of these parameters, we can better probe this parameter space with N-bar oscillation or directly with the LHC. So as usual, it's important to have both kind of experiments to set complementary constraints. Here we can see the same thing. Here I'm simply plotting the coupling versus the Squark mass. So when the coupling is low, this LHC constraint dominate, while if you raise this barrier number violating coupling, of course, then barrier number violating observables give the dominant constraints, and as you can see, they can really already exclude up to 2 TeV or so our Squark masses. And if we go to an extreme case, if we take even order 1 couplings for the barrier number violation and order 1 flavor violation, the situation becomes like this. This is now TeV. So this shows basically the potential of this kind of experiments of testing 3-level new physics that gives rise to an N-bar oscillation with large couplings. So in principle, you see, we can already exclude scales which are of the order of hundreds of TeV. And you can have a substantial improvement by the observed experiments, up to 1000 TeV or so. So here I'm plotting the same thing, this time just setting the barrier number violating coupling to 1, and plotting the oscillation lifetime as a function of the Squark mass. And here you see the present bounds and the projector sensitivity. While these bands give you the feeling of this infamous hadronic uncertainties I was mentioning before. But you can see anyway, there is a lot of room for improvement for this new experiments. So in principle, we can really even go up to, again, 1000 TeV in testing this kind of models. Okay, so I think I'm running out of time, so let me just mention here very quickly that this was just one possible way of giving rise to N-bar oscillations. If you have a look at the paper, we collected several more diagrams that do the job. This is an example of a loop-induced N-bar oscillation, which requires electroweak interactions instead of strongly interacting supersymmetric particles as before. So here you have further loop suppression, but flavor violation is automatically given by these vertices, by the ordinary CKM matrix. So in this case, you don't have to assume anything. You don't have to assume a source of flavor violation beyond the one that it's already present in the standard model. But the effect is much smaller. So in terms of, but also the bounds are much weaker from the LHC. So here I'm showing the present constraint from N bar and the possible improvement by the proposed experiments. Anyway, also here we can test squark masses up to order 2 TeV if the coupling is large. Okay, this brings me to my conclusions. So I just show you that this future neutron anti-neutron experiment proposed that the ESS has indeed the capability of probe by number violation beyond the present constraints. So we worked in a specific setup where, as you can see, different information from different physical processes are required to assess the sensitivity of the experiments. We have on one side flavor constraints, on the other side LHC constraints, dinucleon decays. So, but even if you consider all these bounds, still, I show you that at least for certain setups of the parameter, you can indeed test the models beyond the present bounds, so even if you're like discover something. And in our example, I mean, what is remarkable is that squarks and gluinos in the multi-TeV range, in principle, can be tested. So this is beyond what we can do at Collider, at least at the LHC. If you are in a crazy situation like that, of course, you can even test physics, which is really beyond the reach of any collider we can dream of. Okay, I stop here. Thank you very much.
Okay, thank you very much, Lorenzo. Let's get back. Stop presenting. Okay, so it's time for questions, I guess. Let's see. Let me remind everybody that you can. Here we go. Give me a second. That there's some funny screen sharing going on. Let's see. Let me. Here we go. Okay, I think it's working now. Okay, very good. Okay, let me remind everybody that you can ask questions via the Q&A on Google Plus and via Twitter. So we already have one question, which is by Roberto Lineros, but I guess that he can make it directly through our audio system. So here you go, Lorenzo. Roberto.
Yeah, thank you, Joel, and thank you to Lorenzo, because it was very interesting, the talk. And I have two doubts. One is because you mostly in your study you constrain this lambda UDS or UDB bottom. Yeah. And my question is if it is possible to go to access to higher other generation, like with charms, or lower mass, but with higher generation.
It's a good question. Let me share the screen again. I should have a backup slide. You can see it? Okay, so for instance, oh, sorry. Here we have another possible electroweak contribution, so which involves a loop of third generation quark and squark. So tops, tops, bottom and bottom. So in this case, the coupling that you can probe, if I mean with an n-bar experiment, and a setup like this is of this one. I don't know if you can see it, but it is basically 313. So yeah, it involves the third generation. While typically diagrams with that for the second generation, so here instead you put the charm, since you need some basically some chirality flip, so you need mass insertions. This would be very much suppressed by the charm mass, of course, compared to the top mass, so it's not going to give a visible effect. But in principle, yeah, even though most of these are basically the models we study, most of them are basically sensitive to the two couplings that I've shown. There is this further contribution which involves a different combination of coupling and a different entry of this lambda double prime tensor. Yeah.
Thank you. And another doubt that, I mean, but this is more like transversal. Do you know, or it's possible to, for instance, this experiment of double beta decay, the detector can be sensitive to such slow signatures? I mean, because this is a rare process. I mean, if you have neutron anti-neutron oscillation.
Yeah, but I mean, in this experimental setup, basically you have a neutron beam. So so you let the neutrons fly, and then you observe you observe is some of the neutrons actually convert into antineutrons. So in this case, you have no nuclei involved. A super Kamiokande, I have no idea actually, but I mean, you know, there you have basically just oxygen. So I don't think you can do double beta decay with oxygen nuclei.
No, but I mean, I was referring that if this kind of rare processes may play a role or may be detected in double beta decay experiment. I mean, because either the double beta decay and either these effects are, I mean, either the neutron anti-neutron oscillation are so rare.
Well, yeah. So but you know, I mean, if I don't think you can do better than Super Kamiokande, which has a huge amount of material and observed for many years. So they had a lot of bound neutrons compared to of course, to the size of a double beta decay experiment.
Yeah, I see.
I mean, they set already constraints at the level of 10 to the 32 years on the.
Yeah, I guess it is.
On the oscillation in the oxygen neutron. So yeah, I think it's.
Yeah, I think because of the mass of the Kamiokande, Super Kamiokande, it's almost impossible for the experiment to compete. I mean, at the level of having something similar.
I wonder about ice cube, but there might be a problem of the energy threshold. Maybe they're not sensitive to. I mean, yeah, this process will be too low energy probably for ice cube. But I mean, if not, you know, they have even more oxygen than Super Kamiokande in principle.
Yeah, they will have to install different apparatus under the ice to block the threshold. To see that, maybe.
I guess.
Maybe if there is someone from ice could listen, maybe can have an idea. Anyway, thank you for. I mean, for my question, I guess that's all.
Thanks to you.
Let's see if there are any other questions. Okay, there's none left on the Q&A, but I have a couple of questions myself.
Please.
So one of them is when you present your initial slides, you present the initial Hamiltonian, right? For oscillations, you don't include an absorptive term. So why is this?
So the decay, you mean? I mean.
Yeah, the width.
Yeah, exactly. Because basically on the time scale of these experiments, our neutrons are to a large extent stable. If you think about it, the free neutron lifetime is about 15 minutes. So I don't know how fast they are, but of course they travel this 100-meter pipe in much less time than 15 minutes, fortunately. But it's true. I mean, in principle, I should take into account the imaginary part here and add the width. Yeah. But of course, for this kind of process, I mean, and this experimental setup is irrelevant.
Right, and in principle, you could also have CP violation, right, on the delta M's.
I guess, yeah.
Now, the other question was you've been using the right insertions. So, is this due to the operator that you're using, or is it possible also to impose left-right operators or left-left operators, or a mixture of left-left and right-right?
Yes. Good point. I mean, here, it's the simplest thing we could do just with right-hand. I mean, generating a fully right-handed operator. Yeah. And of course, as you were mentioning, then you have to assume a source of flavor violation in the right-handed squark sector, which is beyond the minimal flavor violation, as we know. But in principle, you can do something different. So you see, this is the full basis of the SU2 invariant operator. So you can have also processes that involve left-handed quark doublets. And in our context, here, these two professors in '86 basically draw this diagram. Let me zoom for you. In this case, you have the flavor violation in the among left-handed spermions, left-handed squarks. And you need a left-right chirality flip. So it's a kind of different contribution also because, different supersymmetric parameters are involved, and you see you end up with a different operator, so involving two left-handed down quarks. But if you look at the results, okay, they're kind of different from the LHC side, but mostly because of my choice of the parameters here. But as you can see, qualitative, we can get to the same conclusions.
Right. Yeah, that's more or less what I. So the orange region. What is the orange region then?
This one, you mean?
The dark orange.
This one is from flavor changing neutral currents. In this case, the most stringent process turns out to be B to D gamma. So from B to D gamma, you can give a pretty strong constraint here. Well, also because here I was taking a quite large value for this flavor violating parameter, above the minimal flavor violating prediction, by the way. So anyway, you need some substantial flavor violation for these processes to give rise to an n-bar oscillation at the observable level. Yeah.
Okay.
But anyway, the flavor constraint is strong, but it's
not as
much as the n-bar constraint.
Cool. I don't know if anybody else on the audience has got a question.
Yeah, I have one that is very naive, I guess. For instance, in this model, the one that you analyzed, you didn't consider or you didn't add because not mostly relevant, I guess, the Gravitino setup. In the sense that usually in models with a parity violation, you can have that the Gravitino can take the role of the dark matter. So my
No,
question
yeah.
was, because it's mass Planck suppressed the decay width, and it
No,
requires parity
it's a good point actually, because I mean, we didn't consider the Gravitino mainly because our philosophy of just defining simplified models with just the ingredients we needed for NN bar alone. But we have to say that for sure the Gravitino cannot be lighter than 1 GeV in this setup. Because if not, then the proton decay to Gravitino. So you have proton decay. Because in this case, you don't need to violate lepton number anymore. So this kind of baryon number violating coupling that I was employing, if you have a fermion lighter than the proton, then it's enough to give you fast proton decay. So the model is completely excluded, or at least it's excluded. Any possible large effect in NN bar oscillation is of course excluded. So any fermion lighter than the proton cannot be there. So also axinos or other kind of exotic things. So this means, for instance, that either you are not in gauge mediation, or you have a very high mediation scale. So you need a relatively heavy Gravitino, or like in gravity mediation, a Gravitino at the with the mass of the same order of the other supersymmetric particles. For sure, not a light one. So I don't think you can have it can be long-lived. I don't think you can have a Gravitino dark matter in this case. So you should rather invoke a completely different sector, like an axion or something like that, for dark matter. Yeah, that's one of the problems of this parity violation. It was lately got a bit of a revival of interest, because of course you can in certain setups you can hide a little bit the supersymmetric particles from the LHC searches because you don't have missing energy. But on the other hand, you have a lot of jets, or in case of leptonic parity violation, you have a lot of leptons, so the bonds are kind of strong. But you lose anyway your dark matter candidate. But we like axioms. So.
Yes, no, very nice. Yeah. So in principle, this kind of setup with Gravitino dark matter is unlikely in this kind of.
I didn't study it in detail, but I would say so. I don't think you can have a long-lived Gravitino.
Thank you.
Okay, I think this is all. We don't have any further questions that I've noticed. Let me check Twitter. No, nothing else on Twitter. Okay, so I hope you all enjoyed this webinar. Well, before I finish, don't forget to subscribe to the YouTube channel of the webinar if you want to watch the seminar again. And well, I hope to see you all on the next Latin American webinar on physics. Thank you again, Lorenzo. I guess that you can now go to sleep. And we'll see you all next time. So let me put.
Good night. Is radar experimental, so that was our starting point. Why? So the present limit on neutron anti-neutron oscillation using free neutrons is this one. It's a limit on the oscillation time of the order of, as you can see, 10 to the 8 seconds. And it was established already more than 20 years ago by this experiment in Grenoble in France. And this is a sketch of what was the experimental setup. More recently, Super Kamiokande in Japan established an indirect limit based on the observation of so based on the fact that, as you know, they have a big tank with a lot of water, so this means a lot of oxygen, so they can set a constraint on the oscillation of neutron bounded within oxygen nucleus. Then, relying on some nuclear physics, you can translate this bound, that, as you can see, is very, very stringent in terms of lifetime, but the processes, as we will see in a minute, are very different if the neutron is a free state or it's bounded in the nuclei. It can be translated to a bound on the oscillation time with his friends who are both theorists and experimentalists from the University of Gothenburg and Stockholm in Sweden. So, as Joel anticipated, the topic is neutron and anti-neutron oscillations. So, why to study such process? So, of course, this is a process that violates the baryon number by 2 units. And we know that baryon number is just an accidental symmetry of the standard model of particle physics. Basically, the Lagrangian of the standard model is invariant under baryon number just because you cannot write any baryon number violating operator respecting all the other symmetries. Nevertheless, it is actually violated, it's broken by non-perturbative effects. But this gives very tiny possible visible effects. So in a sense, if we observe any process violating the baryon number, it's a clean signal of new physics. So this is the first reason why we might be interested in looking like processes of neutron to anti-neutron oscillations. Furthermore, we know that baryon number violation is one of the requirements for having a successful baryogenesis, so to produce the baryon asymmetry in the early universe that then we observe today. So we expect that any extension of the standard model of particle physics will
the transmission later in our YouTube channel. Let me tell you also that we have a WordPress page where we also centralize all the information. I think you can see it right there. Okay, it's not very difficult to remember, right? Law physics, WordPress. So okay, let's get to business. The speaker is Lorenzo Calibbi, and he's currently a senior research associate in the Institute of Theoretical Physics at the Chinese Academy of Science in Beijing, China. So he's practically giving this webinar close to midnight. So I guess we should be very grateful for Lorenzo to give this talk, right? So Lorenzo received his PhD from the University of Padua and has carried out postdocs at CISA, at the Max Planck Institute, and the Université Libre of Brussels, right? And the title of his talk is Neutron Anti-Neutron Oscillations as a Probe of Supersymmetry Beyond the LHC. So let me present Lorenzo. Let's see, present to everyone. Here we go. We're all yours, Lorenzo.
Hi, hi to everybody. Thanks, Joel, for the presentation, and yeah, thanks for inviting me to give this seminar. So I think now I should just share my screen somehow and show you my slides. Can you see it?
Everything good, everything good.
Okay, so here we go. I'm going to present a recent work that I've done in collaboration with
quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Okay, hello everybody. My name is Joel Jones from the PUCP in Lima, Peru, and I'll be today's host of this webinar in the Latin American Webinars of Physics. Today we have a very interesting talk about neutron-antineutron oscillations in supersymmetry. But before we begin, let me remind you that you can ask questions via the Q&A in Google+. These questions will be answered at the end of the talk. Or you can use a hashtag to ask us questions on Twitter. The hashtag is this one. This one, LAWAP. Okay? So that's that. Remember also that if you miss any live transmissions, you can watch.
Will give substantial baryon number violation for this reason. First process that we can think of as baryon number violating process is, of course, proton decay. As we know, this has been searched for since many years, and present constraints are already very stringent on the lifetime of the proton. And this process is, of course, requires the violation of baryon number by 1 unit, but also violation of the lepton number, simply because for conservation of spin, basically, a proton cannot decay to anything else than a lepton. So if instead we have a theory that gives substantial baryon number violation but no lepton number violation, the only new effects we can observe arise at a level of delta B equal 2. So violation of the baryon number by 2 units. And processes of these kinds are precisely neutron-antineutron oscillation, and as we will see later, possibly also dinucleon decay, so the decay of 2 nucleon particles inside nuclei. The main motivation for studying these processes, or for reviving this process that has been studied quite extensively in the past, but not so much lately in recent years.